What is graph theory? In mathematics, graph theory is the study of graphs, which are mathematical structures used to model pairwise relations between objects. A graph in this context is made up of the vertices, also called nodes or points, which are connected by edges, also called links or lines. What is the use of graph theory? Graph theory is used in sociology, for example, to measure actors' prestige or to explore diffusion mechanisms. Graph theory is used in biology and conservation efforts where a vertex represents regions where certain species exist and the edges represent migration path or movement between the regions. Who is the father of graph theory? Leonhard Euler was a Swiss mathematician, physicist, astronomer, geographer, logician and engineer who made important and influential discoveries in many branches of mathematics, such as infinitesimal calculus and graph theory, while also making pioneering contributions to several branches such as topology and analytic number theory. He also introduced much of the modern mathematical terminology and notation, particularly for mathematical analysis, such as the notion of a mathematical function. In this case, we're traversing an undirected graph. Obviously, if the graph was directed, one would simply follow the direction of the edges. There are a couple different types of traversals, so be careful of the wording. These are a couple most common graph traversal terms, what they mean. Walk, a graph traversal. A closed walk is when the destination node is the same as the source node trail. A walk with no repeated edges. A circuit is a closed trail path. A walk with no repeated nodes. A cycle is a closed path. Building on the concept of traversals, one can also send messages across a graph. All of Sam's neighbors are sending him a message, where T stands for the time step. Sam can choose to open his mailbox and update his own information. The concept of propagating information throughout a network is super important for models with attention mechanisms. In graphs, message passing is one way we generalize convolutions. More on that later. Having learned all this, you now have a basic understanding of graph theory. Any other concepts important to geometry will be explained as they come, but in the meantime, there is still one last topic concerning graphs that we need to cover. We must learn how to express graphs computationally. There are a couple ways one can turn a graph into a format that a computer can digest. All of them are different types of matrices. Incidence matrix, I. The incidence matrix, commonly denoted with the capital I in research papers, made up of ones, zeros, and 1s. The incidence matrix can be made by following a simple pattern. Weighted adjacency matrix, A. The adjacency matrix of a graph is made of ones and zeros unless it is otherwise weighted or labeled. The adjacency matrix of an undirected graph is therefore symmetrical along its diagonal, from the top left object to the bottom right. Adjacency matrices of directed graphs only cover one side of the diagonal line, since directed graphs have edges that go in only one direction. An adjacency matrix can be weighted, which basically means each edge has an associated value attached to it, so instead of ones, the value is put in the respective matrix coordinate. These weights can represent anything you want. In the case of molecules, for example, they may represent the type of bond between two nodes, atoms. In a social network like LinkedIn, they can represent first, second, or third, order connections between two nodes, people. This concept of weights for edges is an attribute that makes GNNs so powerful, they allow us to take into account both structural, dependent, and singular, independent, information. For real-world applications, this means we can consider external as well as internal information. Degree matrix, D. The degree matrix of a graph can be found by using the concept of degrees covered earlier. D is essentially a diagonal matrix, where each value of the diagonal is the degree of its corresponding node. Notice that the degree is simply the sum of each row of the adjacency matrix. These degrees are then placed on the diagonal of the matrix, the line of symmetry for the adjacency matrix. This leads nicely to the final matrix. Laplacian matrix, L. The Laplacian matrix of a graph is the result of subtracting the adjacency matrix from the degree matrix. Each value in the degree matrix is subtracted by its respective value in the adjacency matrix as such. There exist other graph matrix representations like the incidence matrix, but the vast majority of GNN applications on graph-type data utilize one, two, or all three of these matrices. This is because they, and the Laplacian matrix in particular, provide substantial information about the entities, an element with attributes, and relations, a connection between entities. The only thing missing is the rule, a function that maps entities to other entities by relations. This is where neural networks come in handy. Euler paths and circuits. A Euler path starts and ends at different vertices. A Euler circuit starts and ends at the same vertex. What is the difference between a path and a circuit? A path is a sequence of vertices with the property that each vertex in the sequence is adjacent to the vertex next to it. A path that does not repeat vertices is called a simple path. Start with an empty stack and an empty circuit, Eulerian path. 1. If all vertices have even degree, choose any of them. This will be the current vertex. 2. If there are exactly two vertices having an odd degree, choose one of them. This will be the current vertex. 3. Otherwise no Euler circuit or path exists. Graph theory. Check. Euler and path circuits. Check. Thanks for watching. Created by Jean Vincent V. Pudadra.